In this video, we are going to discuss about data transfer instructions of 8086 microprocessor or data copy instructions of 8086 microprocessor. Data transfer instructions are mainly useful in order to transfer the data from source to the destination. From source to destination, in order to transfer data from source to destination, we use data transfer instructions. Here the source and destination may be either memory location or register. So by using data transfer instructions, we can transfer data between two memory locations. We can transfer data between two registers. We can transfer data from memory location to register. We can transfer data from register to memory location. So by using data transfer instructions, we can do all these activities. Now let us see what are the different types of data transfer instructions. So we have different types are there. The first one is move instruction. The second one is exchange instruction. Exchange instruction is the exchange instruction. It is denoted by X, C, H, G. Third one is LEA, load effective address. Fourth one is LDS and LES, load data segment, load extra segment. Next one is LAHF, load accumulator higher order byte into the flag with flag. Next one is SAHF. Next one is push. Next one is pop, and the last two are push F, pop F. So totally we have 10 data transfer instructions are there. In this video, we are going to discuss all the instructions in detail with the help of the examples. The first one is move instruction. Move instruction. The mnemonic for the move is MOV. The symbol for the move instruction is MOV. So move instruction is useful to move the data from the source to the destination. So here the syntax is move destination comma source. So by using move, we can transfer the data from source to destination. Here the source and destination may be either memory location or it may be some register. Source may be some immediate data also. Let us see some examples. So move AX comma BX. So this instruction moves the contents of BX to AX. Now AX register contains the contents of BX register. And let us take one more example. Move AL comma. AL means the size is how many bits? 8 bits only. 1 to H. This is hexadecimal number. So 1 means these are digits. Each digit represents 4 bits. Now AL contains 12. Whenever this instruction is executed, then AL contains 12. Now let us see one more example. Move AX comma 1234H. So here this is immediate data. So whenever the statement is executed, then 1234 will be moved to the AX. Now AX contains 1234. So here also 12 is nothing but immediate data only. Whereas if you place them in a square bracket, then it will become the address. Now here 2000H is specified within the boxes, square brackets. Now what will happen? The operand available at 2000 will be moved to the AX. Let 2000 memory location contains an operand called 1234. So now 1234 will be moved to the AX. Let us see one more example. Move AX comma within the square brackets SI. So SI means source index register. Now SI content will be moved to the AX. Let we have SI register contains let ASI register contains 1, 2, 3, 4. Now 1, 2, 3, 4 will be moved to the AX register. So this is about move instruction. Now let us see the next instruction. So what is the next instruction? Exchange instruction. Exchange instruction is represented by the mnemonic XCGH. So exchange instruction exchanges the contents of the source and the destination. So here also the syntax is same only. XCGH, destination comma source. So the contents of source and destination are exchanged. So here the source and destination may be either some memory locations or some registers. Okay, XCGH, AX comma BX. Now what will happen? The contents of AX and BX will be exchanged. Let initially AX contains 1, 2, 3, 4, BX contains 5, 6, 7, 8. So after execution of this instruction, AX content will become 5, 6, 7, 8, whereas BX content will become 1, 2, 3, 4. Okay. Likewise, we can perform exchange operation between memory locations also. So AX comma, let here we have 2000H. 2000H. Now what will happen? Let 2000H, let AX content is 1, 2, 3, 4, whereas 2000 memory location content is 5, 6, 7, 8. Now what will happen? AX and this 2000H content will be swapped. Okay. So after swapping, after exchanging, what will happen? AX content will become 5, 6, 7, 8, whereas this 2000H content will become what? 1, 2, 3, 4. So this is about exchange instruction. Now let us see the next instruction. The next instruction is LEA. LEA. LEA stands for load effective address. Load effective address. Load effective address of the operand into the register. Load effective address of the operand into the register. Let us see an example for this. LEA. Let the register is AX. Let the memory location is 2000H. So now what will happen? So this is the effective address. 2000H is the effective address. Let 2000H contains 1, 2, 3, 4. Now 1, 2, 3, 4 will be loaded into AX. Now AX content is 1, 2, 3, 4. Okay. Load effective address of the operand into the memory location. Let 2000 contains 1, 2, 3, 4. So that 1, 2, 3, 4 will be loaded into EX. Let us see the next two. They are LDS and LES. LDS stands for load data segment. Load data segment. Whereas LES stands for load extra segment. Load extra segment. So data segment and extra segment contain some operands. So here the meaning is load data segment with the content of the memory location. Okay. So LDS, AX comma, let AX is the register we are using in the data segment. So LDS, AX comma, let the memory location is 2000H. So now what will happen? Load data segment register with the content of the memory location. Let 2000H contains 1, 2, 3, 4. Now that 1, 2, 3, 4 will be loaded into AX. AX is nothing but a general purpose register which is used in the data segment. Just like the LDS, we can also use LES. So load extra segment with the content of the memory location. Let the memory location is BX, comma 3000H. Now here BX is the general purpose register which is used in extra segment. So now what will happen? The content of the 3000H will be loaded into the BX. Let 3000H contains 5, 6, 7, 8. So now 5, 6, 7, 8 will be loaded into the BX. Okay. So this is about LEA, LDS, LES. Now let us see the next one. That is LAHF. 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 LAHF means load. AH means what? AH register. We know that load AH register with flag register. Okay. So AH stands for AH register, L stands for load, AH stands for AH register, F stands for flag register. We know that AX register size is 16 bits. AX is made up of two registers. AX mainly contains two registers, AH and AL. So the size of AH is 8 bits, the size of the AL is 8 bits. So AH stands for accumulator higher order byte, whereas AL stands for accumulator lower order byte. Whereas the size of the flag register is 16 bits. 16 bits. LAHF means load AH register with the content of the flag register. But what is the size of the flag? 16 bits. So what will happen is the lower order 8 bits of the flag register will be loaded into the AH register. Okay, will be loaded into the AH register. So this is about LAHF. Load AH register with the lower order 8 bits of the the flag register. Okay. Now let us see the next one. SAHF. S means store. Store AH register in flag register. So previously what we have done is, after executing this instruction, AH register contains the contents of the flag register, the contents of lower order 8 bits of the flag register. But here what we are doing is, we are storing AH register content in the flag register. We are storing the content of AH register in the lower order 8 bits of the flag register. Let AH register contain some content. So that content will be stored in the flag register. So that is the difference. So load means that content will be stored in AH register, whereas store means we are storing the content of the AH register in the lower order 8 bits of the flag register. So that is the difference between load and the store. Now let us see the next instruction, that is push instruction. So push pop, push F, pop F. So if you understand push and pop, then push F and pop F will become quite easy. Let us see about the push. So push instruction is mainly useful in order to push the contents of memory location or a register onto the top of the stack. So we know what is a stack. Stack means a collection of items. Stack works based on the principle of LIFO. LIFO stands for last in first out. So the element which is inserted last will be deleted first from the stack. Let us draw the diagram for the stack. Let the stack contains 3 items. Let the first item is 10, second one is 20, next one is 30. Let this memory location is 2000 EH, next location is 2000 DH, so decrementation of the address. So 2000 CH, so decrementation of the address. Here we use a stack pointer. Stack pointer always points to the topmost item. Now SP points to the 2000 CH. So here for push operation, what will happen is, for push operation, stack pointer will be decremented by 2. For push operation decrements stack pointer by 2. SP will be decremented by 2 and stores 2-byte operand. That means and pushes 2-byte operand onto the stack, in stack, and stores 2-byte operand into stack. So first what will happen is, first higher order byte will be stored. First higher order byte will be pushed. Higher order byte will be pushed and it occupies high address. So next low order byte, lower order byte will be pushed and it occupies lower address, So let us see an example. Lower address. Let here we are executing this operation. Push. Push AX. So here we are pushing the contents of AX onto the top of the stack. So here register capacity is 16 bits, 16 bits, let register contains 40, 50. So here 40 is nothing but higher order byte, whereas 50 is nothing but lower order byte. Already we have seen this. AX means combination of AH and AL. So 40 means higher order, whereas 50 means lower order. Okay. Let us assume that here the stack can store only 8 bits, 1 byte of the information. But here we have 2 bytes. Okay. So now what will happen is, so first, let us see this explanation. First higher order byte will be pushed. So here we know that stack push operation means we have to decrement the stack pointer. Okay. So previously stack pointer is at the 2000 CH. Now what will happen is, we have to decrement the stack pointer one more time. So now stack pointer will be at 2000 BH and we need to store the higher order byte. So what is the higher order byte here? 40. So 40 will be pushed. So that means we have performed the decrementation once. So next we need to store 50. Here 40 is stored at higher order address. So this B is nothing but higher address. Next we have to insert, we have to push this 50 into the stack. Okay. So we have to perform the decrementation one more time. Okay. So decrement the stack pointer one more time. Now the stack pointer will be at 2000 AH location. Now let us push the next lower order byte. Next to push 50 one more time. So that means here we have decremented SP one more time. So that is the point we explained here. For push operation, SP is decremented by 2. SP is decremented by 2 and stores 2 byte operand into the stack. So what is the 2 byte operand? 40 is 1 byte, 50 is another byte. Okay. It stores 2 byte operand into the stack. And let's see the next point. First higher order byte will be pushed. 40 is nothing but higher order byte. So first that is pushed and it is stored at high address. 2000 BH is nothing but high address. Next lower order byte will be pushed and it will be stored at the lower address. So AH is nothing but lower address. Now let us see one more instruction, that is push F. So push F means instead of the register, instead of the general purpose register, here we have to push flag register. So push F means push flag register onto the top of the stack. Push flag register onto the top of the stack. So for push operation, what will happen? Push operation decrements SP by 2 and stores the 2 byte operand into the stack. Why? Because we know that flag register size is 16 bits only. It also contains 2 bytes. Okay. So first higher order byte will be pushed and it occupies higher address. Next lower order byte will be pushed and it occupies the lower address. The explanation for the push and push F both are same only. So push means we are pushing general purpose register information, or we can push the content of the memory location onto the top of the stack. Whereas push F means instead of pushing general purpose register content, here we have to push flag register content onto the top of the stack. We have to push flag register content onto the top of the stack. That is the only difference. And the next two are what? Pop. Pop is entirely opposite to the push operation. So pop means we have to pop some content from the register. We have to pop content from the stack and that content will be stored in a register. And the corresponding popped content will be stored in a register. Here we know that here for push operation decrements SP by 1, whereas pop operation increments SP by 1. I'm sorry. Push operation decrements SP by 2, whereas pop operation increments SP by 2. So first this item will be popped, okay, and then what will happen? This address will be incremented. So after A we have B. Next this item will be popped. So what will happen? One more time incrementation will be done. Now now the stack pointer will point to this location. Now those popped items will be stored in the register. So how many times we have done the incrementation? Twice. So pop operation increments stack pointer by 2 and stores the corresponding popped items in the register. So pop AX. Pop AX means what will happen? The popped items will be stored in the AX register. Okay. So that is about pop operation. Whereas pop F means what will happen? After popping the corresponding items, those items will be stored in the flag register. Instead of the general purpose register, the popped items will be stored in the flag register. That is the only difference. So here in POP-F also what will happen, it decrements stack pointer by 2. Okay, so this is about data transfer instructions or data copy instructions of 8086 microprocessor. So this is about data transfer instructions of 8086 microprocessor.